Okay, so let's start where we left yesterday. I was giving a very, very quick survey of different routes towards the construction of the theory, just so that you have an idea of what people are trying to do in terms of strategies. So, and yesterday we discussed the strategies that depart from the traditional route of take the classical theory, quantize by whatever strategy, canonical, covariant, going to the lattice, and related. We have seen already yesterday that even if you start in that conservative manner, you end up, if you manage to make any progress at all, with structures and a perspective that is necessarily different from the original conservative one, because the type of mathematical structure you end up using do not really resemble just quantum fields in the continuum. You may end up not working with a smooth manifold, and so at the end of the day, even the conservative strategy is not just about putting hats on smooth fields, whatever that means in practice. The other route I was mentioning yesterday as a possible logical alternative is to say, okay, the perturbative quantization of continuum GR doesn't work. So, but instead of trying to just bypass any perturbative approach and go non-perturbative, like in the other formalisms, maybe the issue is that these are not the really fundamental degrees of freedom, or at least they're not enough. Maybe you have to add degrees of freedom still at the continuum level and still within a perturbative framework. Maybe you just need more degrees of freedom, more symmetries, and so on. Yes?
Why do you say more degrees? What I mean, it makes sense, but couldn't we have a theory which has less degrees of freedom but different ones and explains quantum gravity? Is this possible, or is it necessary that we have more degrees?
Can you wait a few? Can you wait a few slides? So I was just illustrating the first two logical alternatives in reaction to the failure of perturbative quantization of continuum GR. Either is a problem with the perturbative approach per se, that you should not expect any perturbative approach to work in the sense of being a good definition of the theory and give you a consistent perturbative expansion. Or you say, no, it has to work, maybe just the wrong type of degrees of freedom. If you make it a bit richer, then you're going to make it. And that's the approach that led, at least at the beginning, to string theory. Now, instead of working with particles and fields, so you enrich the structure, you have extended propagating degrees of freedom in the form of strings, you have additional symmetries, supersymmetry. Then you also end up adding dimensions and a bunch of other ingredients, but the idea was, okay, we can show, it's not a proof in the sense of mathematical physics, but almost you can show that with these additional ingredients, you can have a consistent perturbative quantum theory of strings. Then you show that you can reduce to standard field theory in some appropriate limit. But then, of course, you need to complete the theory at the non-perturbative level, and that's the idea of M theory, because you can show that a lot of extra structure arises in a non-perturbative regime, the branes, a bunch of dualities between different formulations of the theory, and this is a number of implications that I will mention later on. But this is one other route. Of course, there is a third option that I didn't mention at the beginning. I started with the smooth fields, and I said, okay, either you just quantize this non-perturbatively, or including the metric, or you add the degrees of freedom, you enrich the formalism, staying in the framework. But maybe quantum gravity is not quantum GR, is not the result of quantizing a classical theory. And in fact, remember at the beginning I mentioned everything we learned from classical GR that we had to take on board, but we have learned other things. One has to do with thermodynamic properties of black holes first, and then space-time more generally. The hypothesis is that any space-time region has in fact thermodynamic properties. And it has been shown already 30 years ago, for example, by Ted Jacobson, that if you have a notion of entropy that you can relate to geometric properties, and that's what happens, for example, with the area law for entropy, that somehow you relate the area of a causal horizon with, or a surface which has specific causal properties, with the entropy of the system enclosed by that region. In that case, in the usual case, is a black hole. So you have a relation between a thermodynamic quantity, entropy, and a geometric quantity, an area. So the entropy becomes a function of the metric. You take that, then you say, okay, but if I look at the region and I ask what is the energy momentum somehow flowing through that region from matter, for example, then you have a relation between another thermodynamic quantity, heat, and another matter and geometric property, the energy momentum tensor. And then in the derivation, with a bunch of other assumptions, including diff invariance, you say, well, let's check what is the resulting equation relating geometry and matter that is the result of translating from the first law of thermodynamics relating entropy and heat or energy. And then you can show that, in fact, the thermodynamic law becomes the Einstein's equations once you rewrite it in terms of matter fields and geometry using the correspondence between the thermodynamic properties, thermodynamic quantities, and geometric quantities, which is quite remarkable. It somehow suggests, again, it's not a proof, there are very few proofs in quantum gravity, but it suggests that first of all, any region of space can have thermodynamic properties, which is already non-trivial, but also that the Einstein's equations are nothing else than the rewriting of a macroscopic effective thermodynamic description of whatever are the microscopic degrees of freedom giving rise to geometry and matter. So somehow the dynamical equations of GR are not fundamental equations for the degrees of freedom. They are an effective macroscopic result. So the suggestion is maybe you should look for different type of fundamental degrees of freedom in constructing a more fundamental theory of geometry and matter. You should not just take GR and quantize as if it was the fundamental theory. It's an important suggestion. Then the whole field of analog gravity system in condensed matter physics has grown a lot in the last 30 years as well. And here the idea is very simple. It's a bit more complicated than this, but the idea is basically that take any fluid, look at perturbations, waves or phonons over a given background flow, any given configuration of your fluid, and you can show that under rather general assumptions and for a variety of systems, the effective dynamics of the perturbations of the waves satisfies an equation of a quantum field theory on a curved background, even though you are in the lab. I mean, your fluid is in the lab. But the background motion produces an effective curved metric that is the metric to which the perturbations couple. You don't see waves propagating on the flat metric of the lab. They effectively couple to a metric that is a function of the density and velocity of the fluid configuration they propagate on. This is true for classical fluids. It works for BEC, for Bose-Einstein condensates, in optical lattices. It's a very general result. And this gave the possibility at the theoretical level and then at the experimental level of simulating in the lab, in a standard quantum many-body system, quantum field theory on a curved background, so gravitational properties as well, like Hawking radiation or cosmological particle production. And they do it. They actually do the experiments on top of understanding at the theoretical level what may go wrong when you go to high energy starting from quantum field theory on a curved background, because you have the equations. But there you also have the microscopic theory. So you can learn a lot about what could possibly happen when you have an underlying new set of degrees of freedom, but your effective description is QFT on a curved background like the one we use all the time. Anyway, this also suggests that maybe we have to look for new type of degrees of freedom and that the old geometric and gravitational story is an effective emergent one. So that's the hypothesis. And there are a number of other reasons to argue for this type of situation. Again, no proofs, many other ways of interpreting facts about semi-classical gravity that admit this type of interpretation. So singularities can be understood as a total breakdown of the overall continuum picture, rather than just something that needs some quantum h-bar correction to be cured. And I mentioned already black hole thermodynamics, and there are many other hints. So the idea is that maybe we have to go for some new set of degrees of freedom, that the whole notion of space-time and geometry and so on is a collective emergent one, not a fundamental one. Remember what I said about classical GR, that if you're not shocked by the idea that gravity is space-time and geometry, and a statement like the volume of this room is X is in fact a statement about the gravitational interaction, then you haven't thought about it. This is an even more radical case. I just told you that maybe whatever notion of space and time you have is in fact a collective approximate emergent one. You are like a fish swimming in some lake, and you use notions of viscosity and turbulence and all of that. And at some point, somebody tells you that there is the underlying atomic or molecular theory, and that the whole fluid is a collective set of quantities, not the fundamental ones. And you should be even more shocked because now you should try actively, especially if you want to do quantum gravity, to think without relying on any notion of space and time, because you want to derive them from something else. From what? Nobody has a clue. I mean, there are suggestions, as we've seen, but yes, so there was a question there, and then another there.
So regarding the Einstein's equations as a question of states, is there any explicit link between the entropy and the graph combinatorics in the sense of a number of microstates, or is it not the right way to look at it?
So we have seen that in the case of black holes, that entropy can be derived by counting microstates. But in order to do that, you have to have some candidate description of the microstates. And so, yes, realizing from a microscopic theory that type of derivation of the essence equation requires that you have some candidate formalism, and then you can check if you can reproduce it. Yeah.
When you say that it's emergent from non-spatio-temporal something, you don't, so there's no space, something similar to space or time, temporality put into the framework? Because
Yes.
in my mind, if you don't put anything that resembles temporality, you don't have to call it temporality, it's something that involves change.
Uh-huh.
I feel like it's impossible to get something that is temporal out of that.
Yes. Welcome to the club.
So, when you mentioned like this Jacobson, this Jacobson gravitational thermodynamics argument, do you are there any instances when you actually need to assume entropic area law and diffeomorphism invariance?
Yes.
Because I thought that diffeomorphism invariance will give you area law because because entropy is the nether charge.
I told you yesterday that this is true in some cases, but it's not totally obvious that for any surface, including an arbitrary surface, and the entropy you're talking about is the one related to the Unruh, like Rindler accelerated observer, you can play the same game.
Okay, so you have to assume it to have the statistical interpretation of entropy, but not to have the quantity.
Not really. For the derivation, you only need to assume that the entropy is related to the area of that surface, which is a function of the metric. So the only step that you need technically is that you need to write the entropy as a function of the metric, the entropy of something as a function of the metric. Then you need to have an energy or heat related to the same surface, which is also, and write it also as a function of matter content and metric. Once you have that, then you write down the first law thermodynamic, and under a bunch of other assumptions, you follow and you check what is the resulting equation for the metric and matter quantities. And that's the Anson's equations. And you need diff invariance to do that. You need a bunch of other minor assumptions. Normally you assume that you are, first of all, you're using equilibrium thermodynamics, but people have generalized to work and some other non-equilibrium properties. You assume, if I remember correctly, second order in the equations, at least as an expansion, and so on. I don't remember now all the precise assumptions. But yes, diff invariance is there as an extra bit.
Yeah. So yeah, I fully agree that diff invariance is what you need. What I have more conceptual issues with is that you need to assume the area level of entropy, because I was under the impression that diff invariance is enough for that.
I'm not sure that's the case for a generic surface in a generic situation like that.
Okay, thank you.
Okay, so if you take this perspective, what is the task? You have to, first of all, postulate or identify some new degrees of freedom, call them atoms of space, call them whatever you like, but they're not continuum fields per se, they're not the metric or other matter fields. Those are supposed to emerge as collective quantities. And I emphasize, I'm talking about emergent space-time, not emergent gravity, because emergent gravity will mean something like in the Sakharov mechanism or in analog gravity, you start from a theory on flat space and you end up with some curved geometry at some effective level, possibly even dynamical, but the only thing that emerges is curvature and therefore gravity. But here the task is really to have even flat space emerging as a collective entity. So the situation is very similar to that of condensed matter. I don't know how many friends you have doing condensed matter. That's a lot of what they're actually busy with. They know the fundamental theory, or they can safely assume that they have it. You know, some Avogadro number of atoms or molecules or other microscopic building blocks, and the whole task is to show the amazing range of collective effective behavior at different scales, different phases, different descriptions, different new type of excitations, and so on. So the task will be very similar. Your quantum gravity model will either postulate or derive or obtain some microscopic quantum many-body system. And the task is to show that gravity, space-time, the metric, the other matter fields emerge in some regime. But again, the quantum many-body system will have to be pretty peculiar because it will not be many bodies or atom-like objects in flat space. Okay. The other thing I want to emphasize is that this type of picture is supported also by existing quantum gravity approaches, even when they start from a more conservative or non-emergent space-time perspective. Because you often end up anyway with degrees of freedom that are not smooth fields, as I've shown in a couple of examples before. And you are in the same situation. You have new type of degrees of freedom. They could be farther or less far away from smooth fields, but they're different. And you still have to show that smooth fields and geometry and space-time emergence under some coarse-graining, averaging, whatever. And again, here, if you ask if the theory you are after is a unified theory of matter and gravity, then here probably yes, but in a different sense. It's not that you put together in a new, more complex entity all the interactions and matter fields, but both will have to emerge from something else. And unless in the fundamental degrees of freedom there is some natural absolute split between subset of degrees of freedom that separately give rise to geometry and matter, unless that happens, then you are going to have some form of unification. But again, it's of a slightly different type than the normal one. What is clear is that in this picture, one or more, if not all, the basic principles of quantum field theory will have to drop. Locality. What do you even mean by locality if there's no space-time at the fundamental level? In what sense you have a local field theory or a local set of interactions? There may be a sense, but it's not the usual spatio-temporal one. Unitarity. There's no time. I'm not so sure exactly what you mean by unitary evolution. Lorentz invariance, any other space-time symmetry, including diff fields, will be emergent symmetries. So something fancy. as I said, this perspective is in fact suggested and partially realized by a number of quantum gravity approaches, wherever they started from. In canonical loop quantum gravity, I told you the type of quantum states you get are in fact combinatorial algebraic, and if you want to try to relate them to geometries, they are, in the best case, so for special states in some approximation, piecewise flat or piecewise degenerate geometries. So quite singular objects from a geometric point of view with respect to the smooth fields of GR. So you have new degrees of freedom anyway. In lattice quantum gravity, you start from that. You discretize continuum GR, replacing smooth category of fields and dynamics with piecewise flat geometries. And then depending on the specific approach, it can be even more peculiar. In string theory, the very existence of dualities between descriptions of the system in one dimension and description of the system in another dimension, which you can map one-to-one, shows that the very notion of dimension cannot be fundamental. Whatever are the fundamental degrees of freedom, and it's not clear, in string theory, they are not defined on a given dimension, which is fixed. And the other dualities have a similar type of interpretation. I mean, mirror symmetry relates descriptions on different topologies. In ADS-CFT, you can argue that at least space, at least one dimensional space, emerges from a description of the boundary conformal field theory. So the gravitational description on a space-time with one extra dimension is an emergent one. Somehow, in a way that people are debating, some spatio-temporal quantities in the bulk are actually reconstructed out of degrees of freedom on the boundary, where you just lack one dimension, so some particular geometric spatio-temporal observables. In fact, we have partial explicit realization of this emergent space-time scenario. One is matrix models. I don't know if you have heard about that. That's for two-dimensional gravity, mostly Euclidean, but it's a good toy model. You write down, I'll give you again the basic idea. You write down a theory of matrices. It's an abstract theory of matrices. You have an action, and the dynamical entity is a 2x2 matrix with two indices. Oh, thank you. How do you know I needed it? So it's very abstract. No fields, no space-time, no manifold. You write down the theory. You write down a partition function. You take a perturbative expansion in terms of the coupling of the order 3 interaction that you have here. You write down the Feynman diagrams. Because of the way you construct the action, the Feynman diagrams have a combinatorial structure that is in one-to-one correspondence with two-dimensional triangulations. You can take each vertex to be represented by a triangle, with the edges being the matrices entering the interaction. You see order 3 matrix. Put in correspondence each matrix with an edge. The interaction glues the vertices of the edges to form a triangle. When you do the perturbative expansion, the Feynman diagrams will have vertices connected by propagators. Now, the vertices are triangles. The propagator will glue the triangles. So that at the end of the day, the sum over diagrams is a sum over two-dimensional triangulations of any topology, because you glue triangles in all possible ways. In Feynman expansions, whatever you glue is allowed, unless you have some global constraint. So you have a theory that is randomizing, summing over two-dimensional surfaces. Well, believe it or not, in the appropriate limit, upon proper critical behavior, you can show that this simple model produces two-dimensional quantum gravity of Liouville type, is called. It's just 2D gravity, which is a super simple theory, so you're not, it's a bit early to organize a party or to book your trip to Stockholm. But you have an example of a purely combinatorial abstract theory of degrees of freedom that a priori have nothing to do with gravity, even in 2 dimensions, which produces in an appropriate regime 2-dimensional gravity. Yes?
Would you have some implicit assumptions about time if you consider propagator?
This is Euclidean. But propagator here just means the inverse of the quadratic kernel. You have the quadratic part in the action, the inverse of that is the propagator. I mean, you can do Feynman expansion with just a one-dimensional integral whenever it's not a Gaussian.
Yeah, okay, that is...
That's what the theory is about. You write down a partition function, which is a particular function of the matrices, or the matrix entries, or the eigenvalues, if depending on in which basis you write everything, and you do a perturbative expansion. And by the way you constructed the thing is a sum over surfaces, and then you can show with the appropriate interpretation of the matrices, of the triangles and so on, that you can relate it to 2D gravity. I mentioned group field theories earlier. Well, they are a generalization of the idea of matrix models. Instead of matrices, you have tensors. And then because 3D gravity, 4D gravity are a little bit richer than two-dimensional gravity, you have to add the degrees of freedom. You add the type of degrees of freedom that you find in loop-Patnook gravity, so group theoretic data with a similar type of interpretation. But again, you do the Feynman expansion, and now you sum over three-dimensional, four-dimensional lattices. And the task is to control that sum and then to show, like in the 2D matrix model case, that in some regime, upon critical behavior, you get an effective theory of geometry, like in the 2D case. But it's the same type of picture. It's a higher dimensional version of that. And in fact, you can show that, at least in some corner, I was mentioning these results earlier, with a number of assumptions and hypotheses, assuming that, okay, now what you're dealing with are the quantum tetrahedra, quantum simplices I was mentioning yesterday. These are the quanta. So you have a quantum many-body system of the simplicial building blocks. Think of them weird Lego blocks. You have a quantum many-body system of that. So what people have done, you assume that you go to a condensate phase of these building blocks. You approximate the full quantum dynamics with mean field, hydrodynamics, exactly like you do with Bose-Einstein condensates. And then you write down equations for simple observables like the total volume of your state, and you have a notion of volume for each tetrahedron, so you just add up the little volume contributions to have a total volume. And then you can show that the equation, the dynamical equation satisfied by this observable, reduces to the cosmological dynamics in GR at large volumes. But the picture is exactly this emergent space-time picture with some candidate building blocks that you can motivate in different ways. Okay, again, I can give you all the details, but it's the point is to just give you some intuition about what people try to do once they have models of this type. Oh, and by the way, you also solve the singularity replacing it with a bounce in this hydrodynamic approximation. Okay, now this was supposed to be the start of this lecture, so I'm already almost half an hour late. Fine. Okay, I gave you a very quick survey of a bunch of ideas and formalisms. Good. Whatever works. Whichever of these formalisms succeeds, what should we expect from quantum gravity? What are very general facts we would expect from quantum gravity? Suppose that you just quantize GR. So your degrees of freedom are the metric, the tree metric, by the way. What you superpose in the canonical picture are three-dimensional metrics or extrinsic curvature, because you have a phase space description underlying the story. It's not the four-dimensional space-time. Well, you're going to have states labeled by the tree metric, just like the states of a particle are labeled by the position of the particle. And you have a Hilbert space, so you superpose. So what it means is that the generic state will encode either exactly or under appropriate superpositions, spatial distances, volumes, angles, and so on. All geometric properties. Then you're going to have observables, which are the promotion to operators to functions on the classical phase space. Maybe this could be the fundamental definition, or it could be some effective intermediate description from some more fundamental degrees of freedom. But at some level, you expect something like this, some geometric operator. And then you have a dynamics, which, as I said, in the canonical picture is some constraint, some operator acting on the state that should be annihilated by it. There cannot be a Schrödinger equation because there's no time, preferred time direction. So it's a constraint equation. Or you have a sum over histories in the path integral language, as I also mentioned earlier, but again, without relying on any external space-time structure as given. If the theory works in some approximation, which is going to be some classical approximation, because now you're dealing with quantum fields, so there's no continuum story to be told, you should show that a classical description of GR and geometry emerges. Okay, that's the template.
But aren't these like strong restrictions? Because can't we have a theory of different degrees of freedom?
Sure. I'm saying that to the extent in which it is a theory of geometry and gravity, maybe just a portion of the degrees of freedom relates to that. Then there is matter, there is maybe other fancier stuff. But to the extent in which you can argue you're quantizing or you have a theory of quantum space-time and geometry, something like that should be there. Together maybe with all sorts of other stuff. And as I said, it could be the fundamental description like this, if the canonical quantization program in the traditional sense was just working, or in some intermediate regime you have a description like this. So suppose that just doing this step, putting hats on smooth fields, including the metric, was working. That would be pretty boring compared to all the rest I mentioned as a possibility. But notice how much is in fact not boring at all, as if the previous lectures in the school were not enough. You're saying that space, time, geometry, any spatio-temporal geometric quantity becomes subject to quantum fluctuation, superposition, uncertainty, contextuality, I mean, you name it. Any standard property in quantum theory would now apply to geometric space-time quantities. In particular, you do not expect that there is an exact notion of localization or events, because that's the determination of at least 4 quantities of the metric. Most likely they won't commute. You should be very lucky that in your framework the 4 quantities you picked up to compute events are actually all commuting. It's not excluded in principle, but it's quite optimistic. Even worse, we have mentioned fluctuations of causality or indefinite causal order. And again, you should keep track of one basic result in classical geometry. The causal structure is almost the same as the geometry. If I know the causal structure of a given space-time, I know almost all components of the metric. I'm missing only one, the global scale factor, the conformal factor. So if the metric in any sense is non-commuting, fluctuating, subject to superposition and so on, causality is necessarily subject to superposition. Because it's the same thing, it's the same information. You can map from one to the other. So you cannot say, okay, yes, let's quantize geometry, volumes, areas, but I want to stay with a given causal structure. It's a mathematical and one could argue logical impossibility. Another simpler way of looking at it. How do you know that 2 events are time-like separated or space-like? Compute the distance. That's the metric. And I mentioned already, your geometric quantities could end up having a discrete spectrum. So where goes your continuum intuition about space and time? Okay. If you go to an emergent space-time scenario, of course, it's worse. There is an even more radical sense in which you cannot rely on the usual intuition. Do you know about the Bronstein cube? Bronstein is the first guy who ever mentioned the possibility of quantum gravity in the 20s, before being killed by Stalin. It was the nephew of Trotsky, I think. I'm not sure exactly why he was killed, but I doubt it was because of quantum gravity. So the Bronstein cube is the pictorial representation of the space of theories. So you have 3 fundamental constants, the Planck constant, the G Newton, the gravitational constant, and the speed of light. And then you can say, if I go relativistic, if I start including all gravitational effects, if I start going quantum, then you move along the various axes. And quantum gravity, the fundamental theory, is supposed to be there, sometimes ambitiously called the theory of everything, which gives me stomach pain. It's a terrible name. Anyway, so this is the picture of physics, fundamental physics, if you are not in an emergent space-time scenario, and you think that quantum gravity is just about quantizing classical general relativity. Otherwise, you will have to replace it at least with a Bronstein hypercube, because if you have a new set of degrees of freedom, there is a new direction that you have to explore, the one of condensed matter, I mean the one of collective effects and cause-graining and increasing number of degrees of freedom, whatever those degrees of freedom are. So let's label the extra direction by n, the number of degrees of freedom. And we don't know really what happens along those lines, because it depends on what are actually the degrees of freedom. But it's clear that the type of problems you have to face are also of a different type. It's not just quantizing GR and then taking classical limits, h bar to 0, which of course is already tricky in standard quantum mechanics. But it's not just that, because you're really changing degrees of freedom. You see the point? And we know from condensed matter that a lot of physics happens along that extra direction, regardless, on top of whatever happens when you take non-relativistic, relativistic, gravitational, non-gravitational, and quantum classical limits. Same picture as before, same emergent space-time idea. So what are the key issues? Identify fundamental degrees of freedom, control the quantum dynamics at the fundamental level, control any classical approximation of whatever is the quantum degrees of freedom, but if they're not spatio-temporal or gravitational directly, then you also have to control the collective dynamics. The continuum approximation is a different direction, is a different type of approximation, and the classical and continuum approximations in general don't commute. Is it clear why? Think of Bose-Einstein condensates. You have a bunch of atoms, quantum. What happens if you take first the classical approximation of the quantum bosonic atoms? That you get a bunch of balls bouncing to each other. You take a continuum limit, go to some collective fluid aerodynamic description, you get a classical fluid, the result of averaging over bouncing balls. You're missing entirely superfluidity. If you have fermionic stuff, superconductivity, you're missing a huge amount of physics. What you have to do, and that's the non-commuting direction, you first take a continuum limit of the quantum atoms. You use the coherence properties and all of that to have a different type of continuum description where you see superfluidity and all of that. And then if you want, you can take the classical fluid approximation. Okay, that's one example, but I can give you many others. Okay, so the important point is these are two conceptually different type of approximations or limits. In some cases, it may turn out that once you take one, you automatically take the other. I mean, there is a range of things that can happen, but they are conceptually different. At this point in the lecture, if not earlier, you can start wondering, okay, but all good, all fancy, is it physics? Any prospect of actually measuring anything, let alone having a proper operational formulation of the theory? Okay, I'm not going to give a set of lectures just on that for lack of expertise and lack of time. But there exists a large field called quantum gravity phenomenology and a large set of results that show possible quantum gravity effects, not just hypothetical, but testable in existing near future, longer future experiments and observations. And there's a huge range of them. Many of them are studied in the context of effective field theory. You add the Planck scale modifications to standard field theory, and you say, okay, in which cases the effects produced by this Planck scale modification can be tested. For example, the most studied example are modified dispersion relations. You take E square equal m square plus p square. That's the relativistic dispersion for a massive particle propagating across the universe. And you say, well, suppose that there is also p cube over Planck energy plus p to the fourth over Planck energy square. You modify the dispersion relations. And you ask, okay, this will modify the way things propagate due to quantum gravity effects, wherever the origin of those effects. We are doing phenomenology. And you just ask, is there any test I can do to rule out things? And the p to the third terms are already ruled out from synchrotron radiation in the Crab Nebula, for example. But there are many such effects. Relativistic thresholds for processes are modified if there are this type of Planckian corrections. So process that you should not observe becomes allowed, or vice versa. And you can then check in cosmic rays or other stuff if you see processes that you should not expect from non-quantum gravity frameworks. But these are those in standard effective field theory language. But then, you can regularize a black hole interior, curing the singularity, and that has consequences. You can modify the early radiation of the CMB, the spectrum, by some Planckian corrections due to whatever cosmological scenario extracted from quantum gravity. And that, in principle, you can test. There are many, really, really many. Here I want to focus once more on the more conceptual aspect so that you know what to look for in the literature once you decide to read. And in particular, the danger of the effective field theory intuition, according to which you ask, what is the scale of quantum gravity effects? At which scale should I expect something to change due to quantum gravity? And everybody will say the Planck scale, right? Why? Because the first thing you should be taught in undergrad is dimensional analysis. So you say, well, if I have gravitational effects, I have quantum effects, and I'm in a relativistic context, I put the typical constants characterizing those type of effects together, and I get a distance scale, a mass scale, a time scale, and a temperature. Temperature if you add also the Boltzmann constant. And I want to say two things about this. It's all good. We start from what we know and we try to have a guess, a good understanding, a good guess of where we have to look for something new. Three things I want to emphasize. First, this is tiny. It's 10 to the minus 33 centimeters. The smallest thing we ever measured or had indirect experience of are the quarks, and they are 10 to the minus 17, 18, I don't remember, something like that. So this is much smaller, first thing. Second thing, theoretical physicists doing quantum gravity are extremely arrogant. And you can see it because we're basically saying that between the Quark scale and the quantum gravity scale, nothing happens. New effects are going to be there. But between the Quark scale and the Planck scale, it's 18 orders of magnitude, or 17, now I don't remember the number, which is the same distance in scales from the quarks to, well, let's say but applies to me more, we are around 1 meter scale. So it's the same separation, the same difference in orders of magnitude. And you are aware, right, by looking around, that there's a lot of stuff happening between 1 meter and 10 to the minus 17. So assuming that there is that desert, it's a pretty strong assumption. That's the second thing. The third thing is more worrying. We extracted the very idea of the Planck scale as the relevant scale from the very theories we know don't work. From the theories we know we have to replace with something else. We relying on classical GR, relying on standard quantum theory, relying on special relativistic effects, we put together the constants, we get the Planck scale. Suppose that any of them is not fundamental, and you modify it. There will be some new scale, some new parameter, and so on. What is the value of those new parameters? So one has to be a little bit cautious about taking the Planck scale as the answer to the question of what is the relevant scale of quantum gravity effects.
So when we say we need to be cautious about the computation of the Planck scale, it's basically based on two things, dimensional analysis and the constants. So if I think about it, that would mean either dimensional analysis would be flawed, or constants are actually not constants, or are there other possibilities? Or is it not the right way to think about it?
All of this, but also now I was more referring to the very fact that each of these constants could be in fact a function of something else, of other type of parameters or constants in a more fundamental theory from which GR emerges as an effective description. Then there is also the fact of the renormalization group flow, the value of this, of each of the, well, G Newton, the others are treated differently, but they may change with scale. So in different regimes, you can actually have a different value. That's another story. But now I was only referring to the caution of relying too much on the effective field theory reasoning of separation of scales, of relying on the specific theories we know too much. And related to this, and concerning phenomenology, the whole idea that quantum gravity effects had to be confined to small distances or super high energies relies exactly on that type of intuition, on the notion of separation of scales, first of all, in effective field theory, and the fact that the Planck scale is the relevant one. So normally you would say that, I don't know, dark energy cannot be of quantum gravity origin because it's a very large scale effect, or dark matter, or other things. You have to look for super high energy, super microscopic phenomena. If you exercise that caution, you start looking at the same phenomena differently. Let me put it in another way. We always say, we have a good description of the world, quantum field theory, GR, but they're just this fancy, strange phenomena that we have no access to, but may require quantum gravity. But we have no strong reason to feel that we need some new theory, necessarily from observations. We have more or less everything under control. Well, strictly speaking, we don't understand 95% of the content of the universe if you put together dark matter and dark energy. So from this emergent space-time, more cautious perspective, maybe quantum gravity effects are staring at us. Or maybe we are surrounded, we already have all the experimental evidence, we're just looking at it in a wrong way. Okay, so the point is not that quantum gravity effects are not testable, or there's no phenomena that will constrain our theories. From my perspective, and maybe because I'm a theoretician, the problem is on the theory side. We failed to make solid enough contact with the existing phenomenological models which are already in touch with observations. Okay, so connecting to quantum foundations. It's clear that we are meeting at some point, in the sense that for all I said, it's clear that basic principles like locality, unitarity, space-time symmetries, and so on, probably will have to be revised. In absence of space-time, even the usual interpretation of quantum mechanics needs to be revised, or at least it becomes even more tricky. Not only the measurement problem, but all the rest. Try to read the book on quantum foundations. without excising, removing any reference to space and time. And then you check if the resulting text still makes sense, or the resulting interpretation is still meaningful. So you can ask how you need to generalize quantum mechanics to deal with quantum gravity, or you can ask in a more proactive way, which generalization is good because it helps or is more suitable for quantum gravity, so for a more fundamental theory. The risk otherwise is that you have all your fantastic solution of the quantum puzzles, which become irrelevant as soon as you change the theory and you go to a more quantum gravity context, because your solution doesn't apply anymore. So we already heard in the rest of the school a number of topics in quantum foundations which have their own motivation within quantum foundation, but become clearly relevant from a quantum gravity perspective. Okay, and this is another picture. Now, still discussing quantum gravity in general, or even gravitational physics in general, I want to connect to the whole story about quantum reference frames and so on from a classical generativity perspective. You've been told about diffeom invariance and the need for a relational description of things and frames and so on. Let me motivate that from a different corner. And I encourage you to read this paper by Giulini to clarify diffeom invariance, background independence. Sometimes you mix the two in the literature, especially popular science. You need a background independent theory, great. And that's because you have diffeomorphism invariance in classical GR. Okay, what do we exactly mean? And where does the problem of time, the problem of constructing observables in GR with a space-time localization come from? Okay, you have diffeos. You have a classical action, general relativity, and you can apply diffeomorphisms to your manifold and then to fields living on the manifold. What does it mean? A diffeomorphism is a smooth map from the manifold to itself. Okay, you can say it's from a manifold to another manifold. When they are related by diffeomorphism, you can actually identify them. So it's a smooth map. Smoothness is a key. As soon as you go to a more discrete, more general context, strictly speaking, you do not have diffeos. So it's a bit less clear what you have to do. When you map from one point to another point in a manifold, it's not a change of coordinates. That will be passive diffeos, so-called. But the active diffeo is actually a map from a point with whatever is defined at that point, tensor fields, vector fields, and scalar fields, and so on, to another point carrying along fields, tensor field, from a point to another. From the physics at one point on a manifold to the physics at some other point in a manifold. Then you have some dynamical equations. This is regardless of the specific theory. You have some equations that depend on your dynamical fields, including the metric, which I collectively call phi. Metric, scalar, some other tensor, some other vector, doesn't matter. And some background structure. It's the topology for sure, it could be the differentiable structure, it could be any other field that you treat as a background. Okay? Collectively, sigma. You have an equation of motion that depends on sigma and is a set of equations for your dynamical fields phi. All good? F equals 0. You would say that your theory is generally covariant if that happens, that the equation upon application of a diffeo on both the fields and the background structures is still valid. Sometimes this is what people mean by diffeomorphism invariance. But this is a purely cosmetic requirement on your theory. Any theory can be written in this language so that it is generally covariant. Newtonian gravity, special relativity, standard field theory in flat space, any theory. The only thing that is required for this to be true is that you are using tensors or differentiable forms or differential forms. It's just the language, because you just need to be able to transform properly every structure you use to define your theory. And then you transform everything on the right-hand side, and you still have your equations. This is cosmetics. Diffeomorphism invariance is a stronger requirement. It's the requirement that if you transform only your fields, keeping the background structures whatever they are, the equations are still satisfied. So you're mapping solutions to other solutions of the equations, of the same equations with the same background structures. Assuming you have written your equations in a generally covariant language, the first statement is equivalent to the second. You can keep your fields the same and transform the background structures instead, and the equation should still be satisfied. This is non-trivial. This is some theories satisfy that and others don't. So let's assume that what I said is not for a subgroup of the diffeos, but for all the diffeos. So the largest invariance group is the stabilizer of the background structures, whatever they are. Whatever transformation, smooth transformations, from point to point leaves the background structures invariant, that's your largest invariance group. From this point of view, what is the way to have full diffeomorphism invariance? Well, either you have strictly invariant background structures, or you simply have no background structure at all. Everything is dynamical. Everything is subject to variation and to some equation of motion. This is the sense, more precisely, in which diffeomorphism invariance is the same as background independence. You have no background structure. Everything in your equation, in your theory, is subject to equations of motion, to some dynamics.
When you say only invariant background structures, what do you mean exactly?
I don't know, the topology. The global topology of your manifold is invariant and maps from points to points in the manifold. If you have a sphere, you have a sphere. It doesn't matter that you describe things along different points and you apply diffeos. Topological properties will stay the same. That's one example.
But physically, is it equivalent to the known background structure?
It's equivalent from the point of view of invariance. That if your equations depend on the topology or not, is two different cases.
Yes.
I mean, if topological invariance enters parameters in your equations, you are going to only use invariant background structures, but you are using background structures. They do influence your equations. So that's different from not having any background structure. Okay? That's it, all simple, as usual. Not so much, because you can always make a background structure dynamical by adding further equations of motion whose solutions will give you back the background structure you had. And this is one example put forward by Kretschmann and Sorkin, I think. I learned it from Sorkin, but I think it was originally from Kretschmann. Take a real scalar field in Minkowski space. Box with the Minkowski metric applied on phi, the scalar field equals 0. Free scalar field, massless, all in flat space. You look at it and you say, well, this is clearly not diffeomorphism invariant. I have a background structure which is my flat metric. So I can write everything in a generally covariant language, no problem, but it's not invariant under diffeos. True. Now you add an equation. You say, well, I don't have the flat metric. I have a general metric. And I make it dynamical. The equations of motion, however, are Riemann tensor of G equals 0. There's only one solution to that, which is the flat metric. But the new set of equations is diffeom-invariant and therefore background independent according to the previous definition. Every quantity appearing in the system, apart from the topology, is dynamical, subject to equations, on top of being covariant. So you have the field and you have your metric. You have two equations, one for the field, one for the metric. They are coupled because the equation for the field depends on the metric. All great, just like in GR. What is special? It's a trick. What is special is that your equation of motion for your dynamical metric has only one solution. You're just pretending. You're making it dynamical, but there's in fact only one possibility allowed by your theory. So it's in fact a background structure that you've promoted, you camouflaged with a dynamical one.
But if you don't fix the signature, you still have some choice for them.
Yeah, here another background structure in the signature, which is also invariant under diffuse. So you have to refine a bit, all good up to before, but let's refine a little bit the definition. A theory is background independent if it is diff invariant. It does not involve any absolute structure, where an absolute structure is either something that is not dynamical or something that corresponds to a single diffeomorphism orbit. Basically just one metric, one possible solution up to all the diffuse you can apply to it. Okay? It's just to say that you have to be a little bit careful with this. Okay, now forget about the technical specific example. And let's look at the implication of this. And again, this is another implication that if you don't think about it, you sleep well. So I'm sorry to ruin your sleep. A diffeo maps points to points, fields at one point on a manifold to fields at the other point. And we just said that the theory is invariant under any such map. What does it mean? It means that it doesn't really matter that you say something is happening at a given location on the manifold, because you can map it somewhere else, and the theory is invariant. Nothing should change in the physics under that. It means that points in the manifold and everything that happens at points in the manifold has no physical meaning whatsoever in classical generativity, and possibly in the quantum theory. Directions on the manifolds, paths on the manifolds. Time is not any time-like direction on the manifold. Space is not any particular space-like direction or localization in the manifold. Now, it's worse than that. So the very dynamical fields we were discussing, the metric with its coefficients at a point, it's a field. So it's a map from manifold to some fiber, right? To the coefficients, the space of coefficients. They are not physical because they're not different invariant per se. You never measure in GR. You're not supposed to measure, and by measure I don't mean in the lab, I mean in terms of what is formally unobservable in the theory. The metric coefficients at a point. You don't measure anything at a point in a manifold. Now, if you were still hoping to sleep, then you should think, okay, wait, there's something odd about this. We use them all the time. Even in relativistic physics, at all times we use the metric field at a point, we choose the coordinates, we look at trajectories, we even say, and God forgives us for that, that a certain trajectory corresponds to an observer that moves in space-time in a particular way. So, how the two things square? Okay, I'll get there. But it's clear that, yeah.
When you say metric, I guess you mean the metric tensor, because
Sure.
we are talking about the coefficients of the metric. This is a specific coordinate system.
No, it applies any map from points to some domain, to some target, because of the dependence on the point, will not be a different invariant quantity. So yes, here I was illustrating with the metric coefficients, but anything that depends on points on the manifold, by definition, will be mapped somewhere else by a diffeom. That's the main point.
I was thinking, for example, the time dilation, that we measure it, and it depends on the metric.
Mm-hmm.
So
It relates to what I was just saying, that, we use it all the time. Why? What's the catch?
yeah,
I'm getting to the catch. Ask me again in a second. But again, here I just want to recall what I said earlier, so I'm working in a little bit of a recursive fashion. I mentioned that there is the problem of time and so on. You see where it comes from. Nothing in the classical or quantum theory can depend on having chosen a particular temporal direction, let alone a certain localization on the manifold, if you want to speak in a different variant language. This clearly gives rise, in classical but also in quantum gravity, to the issue of observables. What are the observables which are diffeomorphism invariant? It's not hard to construct some of them. You take any density, like the volume density at a point, you integrate over the whole space-time, the whole manifold, that quantity is going to be invariant. The same is true if you insert observables, some other function of the point, and you integrate, you average over the whole manifold. By construction, that's invariant under diffuse. The point is that, first of all, many of this stuff tends to diverge. Okay, so mathematically you have an issue. But the physical point is this is not local information. This is not the space-time information. This is something that is average over all of space-time. It corresponds to nothing we actually try to measure or do physics with. You see the issue? So it's not just the formal one. Please exhibit to me some different variant observable. The real task is to exhibit a different variant observable that is interesting. And it's somehow useful to do space-time physics. So what are local different variant observables? And in fact, what do we mean by local? If it cannot be local on the manifold. So define at a point. So
Shall we leave on a cliffhanger?
yeah, I'll stop at the end of this slide. So the local different variant observables are usually constructed using the so-called relational strategy that has been mentioned a few times. And the idea is the following. You have to use some reference system, but it has to be a physical one, some particular subset of dynamical degrees of freedom, because you don't want to break different variants, so you don't want to introduce some absolute structure. You want to use some physical set of degrees of freedom that transforms under diffuse covariantly, and you use it to define what you mean by an event or a localization in space and time, and to express all the other observables, all the other quantities as a function of it. These dynamical quantities written as a function of other dynamical quantities, if you do the construction correctly, will be different variant and will admit a space-time interpretation if you're using a nice physical frame. So you are defining what you mean by time, space, event, point by some physical system. To go back to why is it that we use all the time coordinates and trajectories on the manifold and time dilation and all of that? I mean, how do we do that? Well, any such physical frame in the idealized limit will reduce, will behave like test fields, or if you want, like coordinates on a manifold. 4 numbers at every point. But it will be in the regime in which you are idealizing away most, if not all, of the physical properties of the system you're using as a frame. And so the relational quantities will have to be constructed taking your dynamical fields and inverting one for the other in appropriate ways, or functions of them, to define a frame, and then the evolution and localization of the others with respect to it. And I'll give you another example in the next slide, in the next lecture. But suppose you have 4 scalar fields defined at a point in the manifold. This is not physical. You have the Ricci scalar function of the metric at a point in the manifold. This is not physical. Suppose you're able to invert these 4 scalar fields as a function of the point, or whatever coordinates you're using. You take it, you plug it back here, and you construct a quantity which is the Ricci scalar as a function of the metric at a point defined by the 4 scalar fields. This is different invariant, and under the interpretation we are giving to the 4 scalar fields as identifying values of a clock and 3 rods, this is a localization in space-time. It's more of a definition of what you mean by space-time, but if you've done the construction properly, it allows you to span what initially was the manifold and to give meaning to points in a manifold. In some idealized regime in which these four scalar fields behave like no scalar field really does, then you can trade that for a particular choice of coordinates. So, from the relational perspective I was discussing, the very fields we use in general relativistic classical and then possibly quantum physics should be unphysical in themselves. What you have to construct are relations between them. And so physical observables will amount to specific correlations in what is called superspace, the space of field values, the only thing that remains when you drop the dependence on the manifold points. And let me show you an example so that you're not scared by the idea until you think about it again. The simplest physical system you can think of, a classical pendulum in 1D. We know obviously everything about it. There's only one variable, which is q. There is time, t. There is an equation of motion. We can write the general solution for the equation of motion. It's a second order equation, so it depends on two constants, two parameters. And there's nothing else to see and to say. You can measure q and t, and you measure q if you have a pendulum, and you have q of t. That's the content, the physical content of the theory, the only observable you can talk about. Now we do something that has only pedagogical purposes and no physical motivation apart from that. You parameterize it. Let's treat q and t as functions of a parameter, tau. So there are two scalar fields in one dimension, in one manifold dimension, labeled by tau. You can write down the whole Hamiltonian phase space formulation of the same system that you just parameterize. You write down the Hamilton equations of motion. You have the Hamiltonian. You write down the old dynamics. And you ask, what sort of symmetries do I have? And of course you have one symmetry, which is one-dimensional diffeos. You can reparameterize from tau to any function of tau, and nothing has to change. The system is the same. Just introduce the parameter on a dependence on a manifold that is entirely redundant. So you have one-dimensional gauge symmetry, different variance. So what do? You have the same problem with observables that I mentioned earlier. Anything q of tau is not physical. Nothing should depend on tau or the points on the one-dimensional manifold you introduced. T as a function of tau is not physical. You never measure t as a function of tau. When I look at my clock, I can say, well, that is t, okay, but it's not t of tau. At which tau I'm looking at the clock? At which value of tau? So what do? Relational strategy. We compute the only diffeomorphism invariant observable we can compute in this system, which is q of t, by taking t as a function of tau, inverting, and plugging it back in q. And of course, I get q of t being exactly the same. Exactly the same quantity I had before. It's the only observable of the theory. The only thing that the theory predicts. So the idea is that these fields are exactly like q of tau and t of tau. And we have to get rid of the dependence on the manifold and of diffeos and rewrite the whole physics in terms of invariant quantities, relations between the fields. Yes?
You say that diffeomorphism invariance indicates what is physical and what is not.
Mm-hmm.
And then, if I understood well, it's q of tau and t of tau that are diffeomorphism invariant.
Q at tau is not invariant. If you apply a transformation, from tau to function of tau, this changes by a one-dimensional diffeo, by derivatives.
But your T doesn't.
Q of t doesn't. That's the relational observable invariant under the diffeo that you can construct. Is the only one, in fact, in this case, and that's what you actually measure. What the theory predicts, what you measure are Q and T separately. Okay, so you would like to do the same for GR and then at the quantum level. So people try that. There are a lot of constructions in full GR in which you try to identify some suitable set of dynamical degrees of freedom, matter fields, for example, use them as frame and try to write everything as a function of those. As you can imagine, it's extremely complicated, and we do not know of any realistic, compelling, deparametrized formulation of full generativity. What happens is normally, if you have if you can identify in your model of the world some global material frame, so something that allows you to invert every quantity in the manifold for it, is not really realistic. People introduce matter fields that do that, but they tend to have the wrong kinetic energy, a lot of unphysical properties if you take them literally as material systems. And vice versa. Any realistic matter fields, you cannot use it as a global clock or a global rod for the whole evolution and the whole space localization. Then you have to use patches and use several of them. But again, the whole construction is complicated. At the quantum level, as you can imagine, that's the whole story of quantum reference frames and so on, everything becomes even more tricky, because a realistic physical system is going to be also quantum. And you have to write everything in terms of a quantum system, and your gravitational field should be quantum as well, and then you have to take care of all the resulting complications. But if you really want to apply the relational strategy, and it seems that you have to, in the full quantum theory, both the geometry or whatever other degrees of freedom underlying geometry and the matter fields should be quantum. Yes.
What is the reason that it's so difficult or obstacle of deparameterization of GR? Why is it why can we not use local frames or
well, there are many reasons, but I give you just one example. Take a scalar field, a relativistic scalar field, and you say, well, forget about space, let me just try to use it as a clock. Okay, so ideally what you want to do, you want to use the field and invert it for some temporal direction that covers the whole manifold. Okay, so that you can say wherever I was writing the metric or some other field as a function of t, some coordinate, now I invert and I use that metric or other fields as a function of phi, your scalar field that defines your time, is your clock. It means that you need a dynamical equation of motion that allows for solutions which are globally invertible for some temporal coordinate. As soon as you put an interaction for the scalar field, it's probably not the case. No, there's no global solution that is always monotonic with respect to a certain temporal direction. Plus, you want to be able to cover the whole manifold. If the manifold is non-compact, you want coordinates that go to infinity. So now is your clock value that has to go to infinity. Now, phi, the field value to infinity, is normally a singular in a lot of dynamical systems. I mean, there are many issues like this. And then if you want to do it for the full frame, it's even more tricky. So the statement is pretty general. Then we can go with specific examples. But the statement is, it seems that the more realistic is your matter system, the less it behaves like an idealized frame that allows you to invert every quantity for every other quantity for it. And so there are global constructions, but again, they tend to use fields that they're not really strictly realistic. Okay, at the quantum level, there are many strategies, and I can point to the literature, but I just want to be aware of what the additional issues are. I mean, when your reference frame, which is a physical system, as well as all the other physical systems you want to localize in space and time, are both quantum. Okay, here is an example of a sector of generativity, cosmology. So just homogeneous fields, both the metric being homogeneous and the scalar fields being homogeneous, so there's only a dependence on time, where you can do the whole construction, go fully relational at both classical and quantum level. And if you look at the type of equations, it is in fact very similar to the harmonic oscillator. At the end, there is only a dependence on a temporal coordinate, because you assume the homogeneity in space, so there's no other dependence on space. And you can do the whole relational construction, and it's GR reduced to a mechanical system by the homogeneity assumption. And the main point is that you end up with a description purely in terms of values of fields without any reference to any underlying manifold. So correlations in what is called superspace, the space of fields. Okay, but I don't have time to dwell more into this. So conclusion, to identify space-time with the manifold on which we put fields is at best an approximation, at best, but it can be misleading. Okay, now I want to draw a couple of conclusions of a more general character in line with the theme of the school about what I just said of relational frames and relational observables and so on. Take it just as evoking some further interesting possibilities to think about. The point I want to make is that one can build an argument that there are serious obstacles, even in classical GR, let alone the full quantum theory, to a framework that is completely intersubjective. And you can argue that there are limits to any notion of strong objectivity, and I will try to clarify what I mean. So let's just to clarify the presuppositions. You have some system observer split. You want a system that is modeled also in its spatio-temporal properties, so you have to use GR or some other gravitational theory. And the fact that there is an observer system split requires that you're dealing with a system in a finite region of space-time. Okay? Otherwise, like the whole universe and the observer is outside, and we don't want to invoke God yet. One way to include aspects of the observer which sits outside is in boundary conditions or the use of specific frames, which are sort of a way to model part of the physics of the observer. But the point is also that if reference frames have to be considered physical, then their physical properties, the interaction with other physical systems, the back reaction on the geometry, quantum properties should be modeled too. Otherwise, you're just pretending. And there is a lot of work in the last, 10 years, more or less, about classical and quantum gravity, mostly classical, in fact, in finite bounded regions. And I'm not going to summarize all of that, but it's really a large bunch of literature there. So people look at what happens when you have a finite region of space, rather than taking asymptotic expansions and idealized situations. A finite region, and you also ask not only what is the physics of that region, including gravity, but also how you can glue together finite regions to obtain more extended regions of space and their gravitational properties. Now, what is the argument? So let me go step by step. First step, the localization of physical systems can be modeled in general. That's how we start doing things in terms of points and trajectories on a manifold. That's what we normally do. And we make explicit everything in terms of coordinate frames. We choose coordinates and we add numbers for the various physical quantities. The diffeomorphism invariance, I argued, that's where we stand, implies that these coordinate frames, and in fact even the manifold points, directions and paths, will disappear in any more fundamental theory because they are not themselves physical. They don't correspond to gauge invariant quantities. So proper definition of localization in space and evolution in time will require a more relational perspective and the introduction and use of physical frames. A truly physical frame will be different from a coordinate frame, and that sounds a platitude, but again, if you think about it, it's not, because it means that you have additional equations of motion for the physical system you're using as a frame, so you're complicating your model. But there will be coupled equations. In other words, your physical frame will back react on the geometry, will interact with all the other systems, including geometry, including the gravitational field. They will also be quantum, so they will be subject to superposition, and whatever reading of the clock will be just a particular eigenvalue of a particular observable, but in general you will have superposition and uncertainty and all of that. And coordinate frames will become physical only as an idealization, in the approximation in which you neglect all these physical properties. Moreover, if you take gravitational physics in a finite region, one can show it requires adding degrees of freedom at the boundary to preserve the symmetry, different invariants in particular, so-called edge modes. Somehow the system becomes enriched by degrees of freedom located at the boundary that take into account the physics of having a finite bounded region. One can show that the edge modes themselves can be used to define a physical frame. In a sense, they give you a preferred choice of a physical frame once you have a physical boundary. But they're dynamical, they back react, they have all the other properties I was mentioning. So at the end of the day, we only have physical reference frame, but we have a more realistic definition of what we mean by local physics. Locality is not a point in a manifold. Locality is localization with respect to some clock and rods that you also model. This means that the only quantities you can compute and are invariant and therefore possibly physical in a gravitational theory with diffeomorphism invariance, the only quantities you can compute are perspectival in a sense. They're always relative to a particular choice of a physical frame, and there's no absolute choice. You have to choose one, write everything with respect to that. Everything you state or predict from the theory will be relative to that.
Yeah, just so I understand correctly, intuitively I feel like your point 5 and 6 are kind of in contradiction, because you say that dynamical edge modes are needed in order to preserve full gauge invariance, but then you also say
They're not unique. They're not unique. Okay. The statement is whenever you have a finite boundary, you need additional degrees of freedom edge modes. Okay. But you can also change the type of edge modes you put. You can have change
so
of
choosing
one particular set of edge modes as a frame is a particular choice of frame. Then you choose another one.
The particular choice of edge modes is not.
And also, you can choose that as a frame, but it doesn't mean that you cannot also, or in alternative, choose another 4 scalars in the bulk and then in the boundary as a frame. So it's an additional natural frame you can use, but it's not the only one anyway, and it's as dynamical and as physical as the others. Now, what happens with general covariance? Now there's no issue with the diffeos mapping points, and so they just disappeared from the formulation of the theory, ideally, if we were able to actually do the whole construction. What happens if you try to compare the rewriting of the theory in terms of a particular physical frame and the theory with respect to another physical frame, with all the physical properties accounted for, possibly even at the quantum level? Is there a map between the two descriptions, which is complete, sort of, you don't miss information? That would be general covariance. You can go from one to the other without missing information. We don't know. It's an open issue. We have arguments for why, at least in the classical case, there should be, but I would say it's still open. At the quantum level, even more. Is what people working on quantum reference frames tend to call quantum diffeos, which I'm a little bit how to say, worried about, because it sort of assumes that whatever transformation you find would be like a gauge symmetry at the quantum level, but I don't see any reason why it should be. If we're really talking about physical frames and not idealized or coordinate frames. It's not diffuse, it's at the quantum level, it's something else. Anyway, suppose that there is such a full physical covariance. Whatever frame you choose, you can always map it to another physical frame. Is there anything which is actually left invariant under that map? Any quantity you compute which is invariant, so it takes the same value in the two descriptions with respect to two physical frames. And there is no reason to expect that there is. This means that, first of all, it's unclear if you can assume that there's going to be complete intersubjectivity. So you can go from one subject to the other, one perspective to another, one frame to the other without missing information. But even if there is, if by objective you mean something that all observers, all perspectives agree on, that's even less clear that there will be any such quantity. Okay, last part of the lecture. In general relativity, we discussed different variants. It's clear that fields, including the metric and geometry, should be fully dynamical. We discussed relational constructions, but there are some background structures. We mentioned already topology earlier. In classical GR, the space-time dimension is fixed. Once you say you are in 4D, you are in 4D. The topology, the signature was mentioned earlier. The signature, the fact that you are on a Riemannian or Lorentzian geometry is fixed, the signature of the metric. Can they become dynamical too in quantum gravity? Now you probably think if that was not bad enough, now we also question these other structures. Sorry. Yes, and in fact we have examples, concrete examples in different quantum gravity formulas where one or the other, if not all of these additional structures on top of geometry become dynamical. Dimension. In one example is in causal dynamical triangulations. You remember was mentioning the discrete lattice path integral for quantum gravity, in which you sum over all possible lattices, assuming them to be equilateral, with the weight given by the exponential of the discrete action for gravity, the Regge action. Okay, you can do the following reasoning. Okay, how do I know that I live in 4 dimensions? And you're not a Platonist, so the fact that you are using a mathematical model that started with a 4-dimensional manifold is not enough. Well, there is some physical process, and you ask if the physical process that is taking place in front of your eyes behaves like you are in a 4-dimensional manifold or in some other dimension. So people consider diffusion processes on these lattices, then sum over, and ask if the diffusion process has a return probability, so you can set up the whole statistical treatment in terms of random walks and probability distributions and all of that. You compute the return probability, you check in a particular regime of small times how it scales with the distance. And the way it scales gives you a definition of what is the effective dimension of your space, because a diffusion process will behave like 1 over distance to the power d, where d is the dimension, is the spectral dimension. This is a particular definition of the dimension of your space on which the diffusion process takes place. So you set up this process in a dynamical triangulations approach, summing over all triangulations, and you ask, you compute this quantity, and you see if it behaves like a quantity in dimension 4, 3, 2, whatever. What happens when you do the calculation is that at larger scales, it behaves like a standard 4-dimensional diffusion process. At smaller scales, or high energy, behaves like a 2-dimensional diffusion process. So the spectral dimension runs with energy or with distance from 4 to 2 And obviously, if you want to run from 4 to 2, you have to pass through fractional dimension. And in fact, you find fractal properties of space-time as well, of the effective space-time. And you can confirm this by other dimensional estimators. And similar results, but a bit less strong, I have to admit, are in other approaches.
How do string theorists?
How do
string theorists claim that there are like 10 dimensions?
There, the logic is entirely different. They don't compute a specific observable. They say, okay, I assume that my worldsheet theory, so my theory of perturbative strings on a given background, on a space-time flat of dimension d, I assume that the worldsheet defines a conformal field theory. They compute what is required to have a proper conformal algebra. There is a standard central charge they can compute, and if you want the symmetry to be non-anomalous, you want to have full conformal symmetry without any anomaly at the quantum level. The anomaly term depends on the dimension of your background space-time. And then they say, well, the theory has to be consistent, so this anomaly should cancel. And it cancels only if the dimension of the background space-time is such and such. In the bosonic theory, 26. In the fermionic supersymmetric theory, 11 or 10. That's how they say that the theory is only well-defined in this sense in a given dimension. And then you have to do something to make it look like or behave like it was in a lower dimensional space. That's the logic. But here is like you start from 4-dimensional simplicial lattices. So the topological dimension is given. You're just saying, well, this is the ingredient, but I don't know if this is what any actual physical observable will correspond to. So I try to compute one. And at least in this case, they find that there is this running of dimension. Okay, what about the signature? Totally different context. You take classical GR, you reduce it to homogeneous configurations, as I mentioned. So you assume that the metric is only dependent on time, on the time coordinate. Then we discuss all the diffuse stuff. For now, just imagine that you're simple-minded, you just have a temporal direction given by some t coordinate. Scalar fields also with a dependence on a t coordinate only, no dependence on space. Okay, homogeneity, like we do in cosmology, the simplest models of cosmology. You can quantize the theory. You can compute the algebra of constraints, the Hamiltonian constraint, the diffeomorphism constraint, and you check what is the Poisson brackets. Okay? You canonically quantize the theory, the classical theory, you compute the algebra of constraints, it should give you the algebra of diffeomorphism, reduced now to the homogeneous setting. Okay? You do that, then you quantize. You realize in this context that the algebra is deformed. So from the classical one to some quantum version of the commutator, the Poisson bracket between the Hamiltonian constraint. So, okay, so the statement here is that from the standard classical constraint algebra, you end up with some modified deformed one where the simple modification encodes the quantum corrections. It's a mechanical model, so it's actually simple to quantize. To derive this is not simple, but you can do it. Now, what turns out to be the case is that when you then start computing solutions and check what happens when you go towards the Big Bang, what would be the Big Bang in the classical cosmological model, this coefficient here changes sign, goes to minus. You will say, well, okay, so what? Changes sign. The point is that the same commutator with a different sign here is the one you would get in a classical Euclidean theory. So what seems to be going on is that you have a Lorentzian gravitational theory, cosmological dynamics, which is quantum corrected because you're able to quantize the system, so there are all sorts of h-bar corrections. But in practice, these h-bar corrections conspire towards the singularity to change the signature, and you don't have any notion of time evolution, relational or not, it doesn't matter. The system behaves like if it was now Euclidean gravity. So again, it could be that it's just an artifact of the symmetry reduction to homogeneous things, but there are arguments for why it should not be. But it's an example of the possibility I was mentioning, that even the signature becomes a dynamical quantity in a full quantum theory.
What's the problem here if it becomes Euclidean when we shrink the space-time? Or like, what's the problem? Isn't it okay if it becomes just Euclidean at the Big Bang?
Well, you cannot speak of evolution anymore, so the type of equation changes the type.
But I mean, if it's, but there's a, no, isn't there like, it would be, okay, but if it's only to a point when it stops, but there's, you know what I mean, there's a regime when there's no evolution, but then there's a regime where it is, right? So maybe it's okay if there's like two regimes.
No, I'm not saying it's a problem. I'm just saying that we have an example, very concrete, of a structure which is a background structure in classical GR, which in the quantum theory, and again in a rather straightforward way of quantizing the classical theory, becomes dynamical. You go from configurations which are effectively Lorentzian to configurations which are effectively Euclidean or Riemannian. It's a fact. I'm not judging, bad or good. I can give you my opinion, but it's not what I'm doing.
Does that mean that at some point it's zero? So
Uh-huh.
how would you?
It's a degenerate geometry. The volume element becomes degenerate at some point in time.
This is so weird.
Sorry?
It's so weird.
If the rest was not weird? Yes, it's... Well, let me say that it would be even more weird if it was not passing through zero.
Oh yeah.
At least you're assuming smoothness in the Poisson brackets.
Honestly, I think I would be more comfortable with that.
Okay, but people have all sorts of perversions, so it's all good. Yeah, no, sure. Again, I'm not judging. I'm just saying the fact is this is what happens, and it's a fact, and that's it. The real question is how general it is. Can we find other examples? What about the topology? Have you ever heard of the third quantization? Boom. Kaboom. Okay. It's a very old thing. Very old, sorry. Despite my extremely young age, this is not so much in the past. It's in the late 80s. I think I was in primary school. Is the idea that take the canonical quantization. You have a wave function on the space of metrics. The space of metrics is itself a metric space. It's called superspace. I mentioned it already. It has certain topology, it has a certain metric structure, but it's the space of metrics and other fields if you have other fields. The space of field configurations if you want. Anyway, so you have a wave function of a tree metric. So it's a function on this superspace. That's the basis of quantum cosmology, canonical quantum gravity, and so on. So somehow you have to define it. For a number of reasons I'm not going to discuss, but good, people said, oh, what about this can be promoted to a field on superspace? And the idea, just like you promote the wave function for a relativistic particle to a scalar field, satisfying the Klein-Gordon equation in the free theory. And so people say, okay, let's write down an action. The kinetic part, the quadratic part, will be just like for the Klein-Gordon field, such that the kinetic operator and the corresponding equations of motion are the Hamiltonian constraint, the Wheeler-DeWitt equation of the canonical theory. Just like the equation, the constraint equation for a relativistic particle is the Klein-Gordon operator. Okay? Same thing. Well, same thing. Now you're on the space of fields. A field on the space of fields. What about the interactions? Well, the free theory will be like in canonical gravity. There is a universe that evolves to a universe, globally hyperbolic. This thing. what about the interaction processes driven by this interaction term? Some higher order monomial in the field on the space of fields. They should produce, that's the idea, topology change. So the universe splitting into two, just like a relativistic particle creates two particles and then annihilate to another particle and so on. So the idea is that you write down a field theory such that, at least at the formal level, when you do the perturbative expansion in Feynman diagrams, the free propagation gives you canonical or covariant quantum gravity on a global hyperbolic manifold, weighted, that's the propagator, by the path integral on that manifold. The other terms describe all possible topology changing processes, wormholes, adding handles to your manifold, space-time wormholes. Now, needless to say, this is a fancy idea, but it was already let's say, difficult to define this thing and to define this thing and the corresponding space of functionals with some scalar product, let alone this action and this path integral, and control this sum over topologies and define this path integral for arbitrary topologies. All of this is super formal. But it's a cool idea, I think, discussing perversions. And the other good thing is that, in fact, we do have realizations of this. They mentioned the matrix model is, in the simpler two-dimensional case, Euclidean, exactly a rigorous realization of this. Remember, we didn't have a function on the space of geometries because we were not in a continuum framework. We're more like an emergent space-time picture. We have a theory of matrices, but what was doing was that the Feynman expansion of that theory of matrices was giving a sum over two-dimensional complexes, so discretized manifolds with metric information, such that in a particular limit, upon phase transitions, will correspond to two-dimensional quantum gravity. And in fact, you could include all topologies. You can compute the same continuum limit when different topologies are contributing and do the whole control over sum over topologies in 2D, Euclidean. So it's not hopeless, it's just that it's complicated. And the mentioned group field theories are, as I said, a generalization of these to higher dimensions. There is a simpler version, which are tensor models. It's the same idea of matrices, generating sum over two-dimensional surfaces. But now you have tensors, with the same principles, generates a sum over higher dimensional lattices. And again, you need to control the sum over topologies and so on. And group field theories are a further generalization when you have a little bit more degrees of freedom.
I'm a bit lost in the fact that the sum on different topologies, is it supposed to represent like the superposition of different trajectories, or is it supposed to give back?
Sure. I mean, for each topology in the discrete context, you also have a sum over triangulations for a given topology. So because you can have many lattices with the same topology. So for each term in the matrix model corresponding to a certain genus, you have a sum over triangulations with that genus. And then you sum over all the triangulation with the different genus and so on. And all of that can be organized and controlled mathematically. In the higher dimensional case, it's not that trivial because you don't have enough topological invariants to classify topologies. In fact, we know that they don't exist. You cannot classify topology. So the way we control partially that sum is different. But the setup is the same. You sum over all possible lattices, including those corresponding to different topologies, in the same perturbative spirit, but in a discrete context, while the original idea of third quantization was in the continuum, but formal. Okay, let's discuss now, and then I close the emergence of space-time, again in some more general aspects. I have 20 minutes, right, but including questions. Okay. I want to spend a few words on the notion of emergence of space-time. The very fact that in classical continuum GR, as we discussed, a proper notion of space-time localization, evolution in time, localization in space, requires a relational rewriting, or may be performed through a relational rewriting, more precisely, can be already called a certain notion of emergence of space, because in order to properly have a notion of space, you need to do something non-trivial. And I told you, I emphasized how non-trivial it is in the classical theory already, to do it for generic configurations. Level 0, suppose that quantum gravity, as I mentioned at the very beginning, is the straightforward result of quantizing the classical theory. Then you're going to have a classical limit. To recover the notion of space-time as we know it, suppress superpositions, or coherently take into account superpositions so that the effect is nice, requires a lot of work, as you can imagine. So already in that sense, there is a very non-trivial step to be taken to have a standard notion of space-time and geometry. And that, I call it level 0 of space-time emergence, which makes you fear that there is worse. So in this sense, you have to go in some highly non-trivial manner from quantum continuum geometries to classical continuum geometries and fields and space-time. So, emergence. Suppose that continuum space-time and geometry are actually obtained from different discrete structures, discrete or some other type of degree of freedom. Then it's a bit up to you at the level of the interpretation. You can say, well, these are just regularization tools. At the end, what is physical is only what I get in a continuum limit. But if you are a little bit more well, you can say optimistic, but you decide that you want to try to give a physical meaning to these new degrees of freedom. It's not just a mathematical artifact. Well, then you are at level 1. There is an extra issue which I already discussed when mentioning the Bronstein hypercube. You have to go from atoms of space, whatever they are, these new degrees of freedom, which are different from continuum quantum fields, to continuum, possibly quantum fields, including space-time notions. And it's going to happen in some approximation. It's not a one-to-one map. So again, emergence, but of a different level, different type. But then we started from a quantum many-body system of quantum degrees of freedom, and we decided that we need to take the approximation in which they collectively interact. What happens when quantum interacting degrees of freedom are added in your system? You start considering more and more, and they are quantum and interacting. In general, you have different phases, different continuum phases. It's quite generic. I mean, the only way to avoid that is that they are not interacting, basically. The system should be simple enough, but it's unlikely that quantum gravity is of that type. So you should expect different continuum phases. Only in one of them, you're going to have, at least in one of them, there should be the possibility of a geometric reconstruction and of classical GR and quantum properties and so on. The others will be non-geometric. At least there's no guarantee that each of them will allow this type of reconstruction. Just like whatever is your theory of a fluid, well, it doesn't work if you are in the solid phase. It's a different macroscopic behavior. So this is a further level in which something should be done concerning emergence of space-time as we know it. Then you can ask, okay, but if mathematically at least I should expect different phases, are they all physical? Maybe the world is organizing as it allows for different phases, only some of which are geometric and have to do with space-time and gravity and so on. If they are physical, well, then the phase transitions are physical. So what is the physics of that? You're just following the logic and you say, well, at some point I can decide, no, this is just mathematical artifacts. Fine, but it's at your risk. There may be physics you're just missing if you decide that you shouldn't look at it. Okay, so you should ask if there is any physical interpretation of the phase transitions themselves. And this is a further level of questions and stuff that you have to worry about. Okay, so the situation from whatever is the fundamental theory of quantum gravity or quantum space-time, call it as you like, to GR in a form that is invariant under Diffie is actually a complicated story. It's not just a limit. Is that a... Oh, that's a question. I thought you were like, no, I don't want to know anymore. Stop it. I would understand.
Would it be envisionable to somehow, like, would it be imaginable to access this p-geometric phase in any way experimentally, or would we only be able to like, measure its effects on the geometric phase by
First of all, this can be answered in specific examples, not in general. In general, it's just a test of optimism. And I tend to be an optimistic person, at least on this stuff. But it's the example I was giving earlier. Suppose you're the same fish swimming in the river, and you're handed a book of atomic physics. You will pose the same question. You will say, yeah, cool. I mean, according to this book, there are different phases. I'm living in a particular geometric liquid phase with all the notions I use, vorticity, viscosity, blah, 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 and which apply nicely in my world. But this says that these are all collective and emergent and they're not fundamental. There are different types of degrees of freedom which have nothing to do with these fluid waves that I'm using to move and send signals. And sure, and you will say, well, can I ever test that? Well, if you're clever enough and you're able to boil the water, staying away from the region you're boiling, or to make ice, then yes, you should be able to test all of that. Maybe indirectly, because you have to stay in the liquid phase. Otherwise, you just don't know how to think. But I don't have an answer to that. You give me a model, we'll see if there is any signature of those type of phase transitions and other phases in the geometric phase. In this emergent space-time story, people started wondering from what you can reconstruct space-time properties and geometry. And an hypothesis that has been explored a lot is the idea that you can extract or put in correspondence geometric quantities to entanglement properties. Now, I don't want to make too strong of a statement, but there is a sense in which this has to be the case. I mean, when you go more precise, of course not. But just take a very superficial view. I'm saying you have some quantum gravity theory in which you have some different type of degree of freedom, which is not geometric, but is quantum. So if you have some quantum many-body system, and you have to reconstruct a notion of geometry and fields and so on, in some approximation. Where else can geometry come from, if not the quantum correlations between your quantum many-body system, your degrees of freedom, your quantum degrees of freedom? So there is a sense in which something like that has to be true. Of course, the difficult task is to make it precise and understand which set of quantum correlations, which quantum observable goes into some specific geometric quantity. But the spirit is sort of very natural. So a lot of examples come from half satisfactory from my point of view context, which is ADS CFT. And it's half satisfactory simply because you can rely on many spatio-temporal notions and quantities on the boundary, and you only reconstruct partially, in a very limited way, space and geometry in the bulk. But you rely on CFT on flat space, on the boundary, and everything is very well defined in terms of concepts you want to use. So it's less of a challenge. But there are many examples of things you do there in which you can relate entanglement measures on the CFT side that relate to geometric quantities in the bulk. The Ryuta-Kanayagi formula for entropy is, or entanglement entropy in the boundary, relating to the area of a specific minimal surface in the bulk is a very interesting example. Again, it's geometry, some geometric quantity given by some quantum measure of quantum correlations in the boundary. It's quite cool. But in the type of example of formalism I was mentioning, you also see this type of situation. Spin networks can be seen as a sort of a quantum many-body system with Hilbert spaces associated to vertices, and in group field theory is even more clear, and you glue these degrees of freedom, you glue these simplices along edges by entanglement. And you can do it very precisely. As I said, each node corresponds to a quantum simplex with a Hilbert space and observables and so on. You have geometric quantities for each simplex, the area of a triangle, the volume of a given simplex, and so on, with operators and spectra. You have a description of a generic quantum many-body state of many quantum tetrahedra. And you can in fact show mathematically that the idea of gluing together two tetrahedra across a triangle is technically maximal entanglement between the degrees of freedom associated to that triangle in each tetrahedron, going to a singlet in those degrees of freedom. And so a graph or a simplicial complex in this language is an entanglement pattern. It's a particular choice of entanglement pattern. And a spin network can be constructed like this, by taking the degrees of freedom of each node and establishing some maximal entanglement pattern. And this is common to canonical loop quantum gravity, group field theory, a bunch of approaches. And you can see then, therefore, that the adjacency relation that you attribute to a graph or to a simplicial complex is nothing else than indeed a pattern of entanglement of quantum correlations. So in this sense, topology at the discrete level is just a restatement of entanglement at the quantum level. But then you can say a bit more. You ask what is a measure of entanglement across two tetrahedra across a triangle. And the simplest measure of entanglement you can give is sort of the dimension of the corresponding Hilbert space on the triangle. And that scales, in fact, with the area of that triangle that you can define independently as a geometric quantity. So there is this type of correspondence. And the same is true for the volume of each tetrahedron. You look at the degrees of freedom of the four phases. They are entangled by some invariance constraint that I don't want to discuss, and the measure of entanglement scales with the volume of that tetrahedron defined independently as a geometric quantity you quantize. So there is a sort of a primitive entanglement geometry correspondence at the discrete level here, and it has been used in a number of works. Okay. I want to leave room for at least a few questions, so I'll skip all of that. You can have similar quantum information theoretic tools and structures at the level of the histories of these discrete quantum structures. And the whole formalism of quantum causal histories and so on, it can be related to the whole notion of spin foam models and quantum processes in the gravitational context. I want to skip all of that, but there will be a lot to say, and I'm happy to discuss about indefinite causality and superposition of causal structures here in a concrete quantum gravity setting, discrete. But I'll skip all of that, including, I'm saying what I'm skipping, the whole story about whether you can have closed time-like loops, if there are ways to suppress them, if the evolution is unitary in any sense, and at which level, and so on. I'll skip that. So this was supposed to be a YouTube video of that should warn you that with enough epicycles you can fit any pattern in the sky. Okay, you believe me, right? Now, what's the point I want to make beyond the metaphor and the funny joke? We should be, again, wary of excessive reliance on the existing paradigm for doing physics, especially if we have already independent reasons to believe that that's just an approximation, that maybe a lot of the concepts it is based on will have to be revised. If look, okay, are there cosmologists in the audience? Sorry. Particle physicist? Okay, just one enemy, 2 enemies in a day is less than my is less than my average. So it's good. It's in fact a good day. From a quantum gravity theorist that looks at theoretical cosmology or particle physics, in fact, and again, just to avoid violence, quantum gravity theorists have, as you have seen, a lot of other problems. It's not that we don't have our dirty stuff and issues. You look at what is going on and you say, okay, we have I don't know, dark energy, and we don't fit, we don't understand why the universe is accelerating and why it seems to be even accelerating in a non-constant manner. If you see all the DAISY results and other stuff, okay, there is something going on. What do people do? You look at what is published. You don't understand the details, but you try to see what the strategy is. The strategy is almost inevitably the following. Let's add the scalar field, then let's add the potential. Let's change the coupling with the other fields, with gravity, with whatever, and see if we can fit what is going on. Not really. Then we change the potential. Then maybe it's 2 scalar fields. Then maybe they interact in another way. In particle physics, don't laugh. In particle physics, it's the same logic. You know, yeah. Suppose, luckily they didn't, but suppose they were finding something at LHC. No, there is some new resonance that we cannot explain. A new particle. And maybe a new particle is not enough. Then a new symmetry. Then, okay, it's complicated. And 2 more particles. And then they're coupled in a weird way. Okay, or we ask to our quantum gravity friends for some crazy idea that we can translate into strange particles and strange symmetries. But the logic is, we have the language of field theory, super successful, super happy. We know it's not fundamental for a number of reasons. None of the more fundamental proposals are solid enough, controlled enough. Okay, that's why I'm saying as quantum gravity theorists, we have our problems. But the logic is, okay, let's keep adding fields, epicycles, and then it fits. Okay, that fits. What does it explain? When you try to change perspective, you can go horribly wrong, of course. But the potential gain is actual explanatory power. And for example, the space-time is emergent, as I already mentioned. All main ingredients of effective field theory will eventually break down. So all the basic ingredients you put in writing down a general effective field theory action will probably break down: localities, space-time symmetries, unitarity, and so on. Separation of scales. I mentioned already the warning, thing that of Planck scale being the extra scale. So you should take it with care, all that intuition. So, for example, dark energy could be one such thing, something that from the effective field theory point of view should have nothing to do with quantum gravity. In fact, the whole problem of the cosmological constant, the way it's normally formulated, arises from saying, well, what else can it be, the cosmological constant, if not the 0-point energy of fields on a given background? It doesn't work. And you say, there is a problem with the cosmological constant. No, there is a problem with the reasoning. It's not that. It's not the value that doesn't match and you have to complicate the story, but within the same reasoning. It's not that. So it could be, for example, that dark energy has a totally different origin in some emergent quantum gravity framework. And we have examples. In the same context I was mentioning earlier, that you have this quantum field theory of building blocks, so you have your quantum many-body system, you have to take hydrodynamic mean field approximations, extract the effective dynamics of geometric observables like the volume of the universe. I told you it seems to work, at least for this simple case, in reproducing the Friedmann equations of GR at large volumes, and replacing the Big Bang singularity with the bounds, well, another thing that seems to be happening rather generically is that the interactions, the microscopic interactions, when written at this hydrodynamic level, produce indeed an accelerated expansion at even larger volumes. It's like at larger volumes, the density of your fluid grows. The density scales, well, the volume of the universe scales with the density, so it's pushed farther. And it looks like, in fact, in specific subclasses of models, it looks like a phantom-like dark energy, something that at least qualitatively is viable. This doesn't prove anything. It just shows that you can find examples in which, from a different perspective, a particular problem that either cannot nicely be solved with the usual field theoretic tools, or it can be solved, but it's unclear whether it has really explanatory power, can maybe get a different explanation. And for phantom fields, we know have the wrong type of kinetic energy. So even if they do fit, is one of those examples in which you say, yes, there is a field theoretic description of this, but this cannot be a fundamental theory as a field theory. You can also fit everything with some modified gravity theory, but when you can choose the function of the metric, then it's an infinity of parameters. So in itself, I'm not surprised that you can fit the data. The question again is what produces this modification of gravity? Okay, the lesson is that you can, in principle, understand from the full theory also super macroscopic phenomena as coming from collective behavior of your microscopic degrees of freedom, and keep it just as a possibility in mind. So I conclude, and the conclusion comes to something that had been said at some point. Oh, I just cannot see how you can think without space and time. I'm paraphrasing. But it's exactly what Einstein was saying, and so it cannot be totally wrong. It can be partially wrong. And Einstein was, probably you can find something that Einstein said on any topic, and possibly saying A and non-A, but depending on where you look. But let me do the same, play the same game. And I think this was maybe the Leiden lecture, I'm not totally sure. I'm paraphrasing, he was just saying, yeah, maybe in light of quantum mechanics, we can think of having a similar discrete, non-field theoretic structure or description for space-time. Maybe we will have to go in that direction. But at the moment, such a program looks like an attempt to breathe in empty space, which fits also with the idea of different phases and so on. So the whole conclusion is that I gave you a survey just to show that painfully and slowly we are learning to breathe in empty space. Okay. Thank you. Try again. So, yeah, give him the microphone. My hearing is bad.
Should I repeat or?
Only the very last part.
Does it make sense in some sense to identify some compatible intersubjectivity between two frames with correlations between those two systems?
If I understand correctly, you're basically asking, let me translate in my own language. So you're basically asking if what will be translatable, or if not invariant from different relational descriptions at the quantum level will be the quantum correlations.
Yeah.
I was saying could be the origin of some geometric quantity in emergent space-time picture. Okay. First reaction, yes, that would be cool. Second, it's hard to, in the context in which I can formulate the story of correspondence between entanglement and geometric quantities a bit more precisely. Nobody has done the construction in a fully relational language, introducing some physical degree of freedom to play the role of frame. So I don't know if those correlations can be written in a relational language and then shown to be at least quantitatively or qualitatively invariant under change of frame. So in practice, I don't know. Third, I would be a bit surprised if they are actually invariant, because in other cases in which, without gravity, the very notion of subsystems and therefore entanglement seems to be perspective dependent or frame dependent. So I'll be very surprised if you go to the quantum gravity case and in fact it becomes invariant. I would rather expect that it becomes even less invariant, not more. Fourth, now that I'm thinking about it, in all of this discussion, we are assuming maybe naive interpretation of quantum mechanics in which the quantum states are just describing something out there and we compute correlations as if there were something out there, forgetting that maybe the quantum state itself is relational or perspectival or depending on a context somehow. And even in that case, there is what I said in point 1, 2, and 3.
What was the last bit you said, sorry?
Sorry?
Sorry, just the last few words you said.
Sorry?
Even in that case, there's still
Yeah, even in that case, the other three difficulties or questions would remain. So I'm still even forgetting that aspect of perspective dependence. I still don't see why the quantum correlations would be invariant for the other reasons I mentioned.
Okay, thank you.
Percolation on microphone is interesting. Yes, I've got like quite a blue sky philosophical question, perhaps a very useless one.
I'll give you a blue sky philosophical answer.
I hope so. So in general, in history of physics, we have had like many paradigm shifts, and one of like a very important ones was when we moved from a heuristic description of nature, like for example Aristotle's natural motion, to the mathematical description. It was like a massive, like radical change in our understanding, but now for a while, it happened a long time ago, and for a while we've been working within this framework of mathematics, mostly based on classical propositional calculus. Do you think it's possible that the problems with quantizing gravity call for another such radical paradigm shift, like some sort of like meta-mathematical shift, when we would have to abandon some of like the most basic assumptions we have about mathematics in general? For example, consider different logic and see if we can build whole new like version of mathematics from this.
So there is a similar worry even at the lower level. I've been assuming mostly standard quantum mechanics as a formalism. Hilbert spaces, operators, some path integrals maybe, some discrete version of that, but more or less I'm not touching the formalism. But I had mentioned that it's quite possible, if not likely, that even the quantum formalism will require some generalization in order to be applied also to space-time and whatever more fundamental degrees of freedom underlying space-time. And that is even less than actually changing logic or extending or modifying logic. So that's one partial answer. The other partial answer is yes, first, unless we have a theory, we don't know what is needed to do it, to have the theory. That's the positive way of replying. The negative way of replying is, yes, so what? We don't work that way. I mean, it doesn't work that way. It's not that at some point we say, okay, we don't have the theory, therefore I should try something super radical, and I think of the most radical thing, and that somehow, as if our ignorance is the argument for going extremely radical. I'm sympathetic with any super radical stuff, but then it has to boil down to a particular strategy, particular model, a particular formalism. So you have an argument, philosophical, poetical, or ethical, that you need to change propositional calculus to do quantum gravity. Not you, I mean you as an abstract entity. Fine, tell me how. And then we see what works, what doesn't, what is the difficulty, we develop that, and we see. So yes, in principle, yes, but there are many other possibilities as well, and everything will have to be judged by the actual results. Partial, because we have to be honest and nobody has the answer, and it's not that it has to fit in the particular quantum gravity formalism I like, otherwise you're definitely wrong. I would like to have the sort of power in the larger theoretical physics community to impose that, of course. Everybody wants to be a dictator, at least for a few days, until they kill you in the coup. But it doesn't work like that. We don't find theories by just postulating some super radical thing. When you say there's been very many paradigm shifts, look at the history seriously. Nobody has been planning a paradigm shift. Nobody was like, oh, this is clearly a situation of crisis, we need a paradigm shift. Where is it? I have it. I had it here, now I cannot find it. It doesn't work like that. So you do things more or less conservative, more or less radical, you try something, you try to seriously to make it work. At some point that happens a paradigm shift, because one strategy becomes successful and you start gaining results and it attracts more people and it solves some particular issue, wins the competition with another radical proposal, because one solves more problems than the other, at least for a while, then it dies, then the other one surpasses. It's a complicated process, and it's collective, by the way. The other thing that you have to dispel is the idea that, I'm a genius, so I got what is the cool, new, radical idea, and I will make it work. And it's a white rabbit. It's not like that. It's a collective thing. You have to convince people, and there's a good reason why you have to convince people, because they will put forward criticism and objections and things that don't work in your fantastic idea.
Yeah, I think I do.
So the answer is yes, but which one? How exactly? Let's discuss a specific proposal, or how we can cook up a specific proposal, and I'm happy to discuss it.
I think I essentially agree with your opinion on this. I like one thing, for example, like you ask if I have like a logical, philosophical, or whatever reason and a proposal.
No, it was a metaphysical view.
Yeah, metaphysical me. Like one thing I could personally think of is like we have seen that there is some sort of problem when we want to, at the same time, abandon the notion of space-time, but we also ideally would like to have a theory that it's in some sense dynamical. There is some notion of changes. So one way you could think of that, perhaps if we were to abandon the notion that P and not P is enforced to be false in your mathematics, then you could try to think of there are legitimate like logical systems when they don't impose that thing, like philosophers won't correlate.
No, I mean, I was coming up. I was going to put forward anyway an example. I mean, there's people who have been trying to use topos theory and intuitionistic logic to formulate models of quantum gravity, as well as higher category theory for quantum gravity models. And I'm on the very, very first paper I read on quantum gravity when I was a kid. Now just to create the mythology when I was in primary school. Blatantly false. Was by Isham, Chris Isham, and Chris Isham has been one of those who has been later proposing topos theory and intuitionistic logic as the proper framework, logical framework for going beyond classical physics, and even to understand better quantum mechanics as a framework or generalize it. in connection to quantum gravity, but also independently of quantum gravity. And there are papers like that. And there is more recent paper like Andreas Döring, Cecilia Flori, I think, left the academia, but she was working on that. And there are a bunch of other people that some of them I know, some others I never did. But people try it.
Oh, thank you. Do you have like a specific paper you could recommend?
I had to think a little bit, but yes.
Thank you.
I mean, not on top. I don't remember the archive number on top.
Yeah, obviously, yeah.
Yes.